And specifically, we're going to talk about nonlinear static problems. So we're going to ignore any time dependence because that doesn't really change what we do. We treat the time dependence with a different integrator, right? So really what we're talking about here is what we do for the static or the stiffness matrix case. So in a nonlinear problem, our stiffness matrix is going to be a function of u. So we have an equation of the form, where u is an unknown. We have a stiffness matrix that's dependent upon u times u, and of course that would introduce nonlinearity in u. So how do we solve this? Well, one way is to use an iteration technique. So we could do something like evaluate the stiffness matrix at the old time step, right? So evaluate it with what we know, step n, and solve for an unknown time step such that we have something like this. And then we just keep doing this, right? We'd solve for new displacements, plug them back in, do it again, do it again. We just keep iterating until some convergence criterion was met. For example, we might look at the change and the change in the solution vector from one iteration to the next over the norm of the change over the norm of the new displacements. And if that's less than some tolerance, say 1 to the minus sixth, then we quit doing it. Right? So if this is a linear problem and we were doing this, what would it be called? So if this is a linear problem, so now k is just a constant, and we're just going to just keep iterating. Maybe Gauss-Seidel, right? So that's what you do in a Gauss-Seidel iteration scheme, right? You just guess the solution vector, plug it in to compute some, plug it in and compute some new displacements. Take those new displacements, plug them back in, and just keep doing it until you get converge, right? That's Gauss-Seidel iteration, right? So let's see what happens if we do this. And so we're going to have because we're solving nonlinear systems of equations, right? It's just when we have a finite element or problem, we have far more than two equations. But fundamentally, it's no different than this, right? We have two nonlinear equations, right? This equation of a circle and the equation of that line. And we want to solve for the roots, right? And there's two roots, clearly, right? One here and one there. So let's try to do something like Gauss-Seidel iteration. So my little black dot right there is my initial guess. Okay? I'm going to plug that into my nonlinear equations, compute a new u, and just do it over and over. So I know it's a little bit hard to see, but what happened was it jumped right over there on the first one, and then it moved a little bit. So so go here. That's my initial guess. One iteration. I'm pretty close. 2 iterations, 3 iterations, 4. And at some 5, 6, 7, the answer doesn't really change. So I honed in on the root. So I found it. Let's try that one with the same procedure. So here I have essentially the same, just the negative of my first guess, essentially the same initial guess, right? First iteration, second. Oh, where'd it go? Went off the screen. So initial guess, first iteration, not so bad. Looks like we're going to get there. Next iteration, it's diverged, it's gone. So to do a Gauss-Seidel iteration nonlinear problem is not a very good technique. If you happen to know exactly what the solution was and you're really close to it, maybe you could do it. But it's not a very robust technique. And so if you actually look at the numbers there, so that's the initial guess. And then you see it just blow up, go unstable. You started getting. Well, clearly these are, the roots are real, and these are imaginary numbers, so it's, something went haywire. Yeah, I have some other comments that you can rewrite the equation, but yeah. So if you rewrite these equations, so they're the same, but just depending on that you rewrite them like that, then you can use that same initial guess and get convergence. But anyway, the point is this is not a robust method for nonlinear problems. So what do we do?